Welcome to Composites 1. This is going to be the first lecture on composites. So let's go over our lecture objectives today. What we try to do today is we try to cover the basics of technology and classification of composite materials. And we are also going to go over metal matrix composites as one of the major categories of composites. And then we're going to cover ceramic matrix composites and polymer matrix composites. Let's get started. Let's define composites or composite material in engineering. A composite material is a material system. Usually it is composed of two or more distinct phases. We can pretty much be able to distinguish these two phases with not much difficulty, whose combination produces aggregate properties different than those of its constituents. So pretty much this definition tells us that if we have a composite material, that means we are going to have more than one material. It's a combination of two or more. There will be a distinct phase between two or more distinct phases, and the combination of these materials, we do it for a purpose, not just for the heck of it. Nobody would combine two materials just for the sake of combining two materials. What we try to do is we try to achieve certain objectives, and that is to achieve a material that has different properties than those of its constituents. So an example of composite material is cemented carbides, and the other one we are very familiar with, plastic molding compounds with fillers, rubber mixed with carbon black. We use them in making tires, and wood. Wood is a material that most people don't think of it as composite, but in engineering, wood is a composite material. It's a natural composite, and of course that is the main difference between wood and other composites that are man-made, what we call synthesized composites. So right off the bat, natural composites versus synthesized composites. Natural composites are those that are naturally occurring in nature, and the best example would be wood. So what are some of the advantages of composites, or what makes composite material attractive? First of all, they can be very strong and stiff, and it is very important for composite material to be lightweight. It's very important because we have certain applications. For example, in the airplane or defense industry, we want to make sure that we minimize the consumption of the fuel consumption, because it's costing industry money, and yet we don't want to sacrifice the strength of what we build. For example, an airplane, we cannot really afford making something that won't last, and it will crash, because these are airplanes, people's lives. So moving away from steel, then we look into different materials, and we came across with composites, because they are strong, they are lightweight, and they are pretty stiff. So knowing all these properties, and knowing that the strength to weight and the stiffness to weight ratios are several times greater than steel or aluminum, of course that composites would be an attractive choice. Also, fatigue properties. When we have a random vibration, or every time we have a low cycle or fatigue, that is caused due to a long-term vibration. This could be in the case of airplane wings, other movable parts that are exposed to certain type of loading that is cyclic, but the magnitude of the loading is not as high as it is for some other cases. So fatigue properties are very important properties when we talk about composites and metals in general. So composites provide an attractive alternative to metals when we talk about fatigue. Also, toughness is often greater. We can also combine them and achieve combinations that one material alone will not offer. For example, is metals, ceramics, and polymers by itself. In the case of metals, steel is the material of choice in many applications, but not in all applications, because sometimes the weight is too much, and it becomes excessive that we cannot build our airplanes out of steel. Maybe some components of them, but most of our airplanes are made of composites, between 50 to 80%, whether by weight or by volume. So that's very important to understand why we are using the composites. Also, applications of composites. That is a very important topic. The composites can be applied in many different cases that other materials cannot be combined. For example, in the case of rehabilitation of our civil infrastructure, composites provide a very attractive alternative as opposed to other types of materials. As with any other material, there are also what I call disadvantages and limitations. Properties of many important composites are anisotropic. What do we mean when we talk about an isotropic material? That is an isotropic. We have an isotropic material and an anisotropic. Isotropic material is a material that properties in every direction, when we model the material in 3D or 2D, in every direction the properties are the same. And for an anisotropic material, this is not the case. An anisotropic does not have properties in every direction of the material in X, Y, and Z. So that could be a disadvantage in some applications. However, it could be an advantage for many other cases. So it's important to understand that. Also, we have a problem here, and that is chemical attack and solvent attack. Some polymer-based composites, again, the key word here is they're polymer-based composites. They are, when they're subject to chemical and solvent attack, then they don't behave well, and they're susceptible to that type of environment. Costs. One of the what I call major disadvantage is composite materials are generally expensive. The costs have been coming down for the past 30 years, but still they are pretty expensive, and that is one thing that make them less attractive at this stage. With the advancement in the material and manufacturing processes and all that, over the years the cost will come down eventually. So that's very important to realize. Also, its manufacturing methods for composites are usually slow and it's costly. That's why actually the composite materials are pretty expensive. So these are some of the major disadvantages. So let's take a look at one classification of composite materials. There are so many classifications out there. One is the traditional composites or natural composites, and the other one is synthetic composites. Traditional composites, they're nature-made. They've been produced by a civilization for many years. An example is wood. We have different types of concrete and different types of natural asphalt, not the synthetic one. On the other hand, we can have modern material systems. These are produced by men throughout using manufacturing processes, and Of course, we produce them separately, then we combine them, we process them to achieve certain results that are desirable for our application. So, what are some of the components in a composite material? Let's talk about major components. Most composites, not all, they consist of two phases. One is the primary phase, the other one is the secondary phase. The primary phase is where we form the matrix. This matrix is what it holds the material together, and this is where we actually build the foundation in which we can bring the secondary phase and embed it into the primary phase. The embedded phase, sometimes referred to as a reinforcing agent or secondary phase, it usually strengthens the composite materials, having the foundation. We add the material to this foundation to provide the material that we would like to have. There are different types of matrix composites. One is the MMCs, or metal matrix composites. These are mixtures of ceramics, in most cases metals, and these are, and examples are cemented carbides and other types. Ceramic matrix composites, CMCS, an example is Al2O3, and these would be embedded with fibers to improve the properties. Shortly, I'm going to take a look at the a composite, a piece of composite, and we could have a better understanding as to what it is made of and how it is made of. Polymer matrix composites, or PMCs, are another type. These are polymer resins. They are again embedded with fillers or reinforcing agents. The examples are epoxy and polyester with fiber reinforcement, and other types of material that have similar characteristics. Functions of the matrix materials include the primary phase, which provides, again, the bulk form of the part or product made of the composite material. These are the foundation. Then we have embedded phase, which we keep the embedded phase in place, usually enclosing and often concealing it. So when a load applies, then what happens? I'm going to shortly take a look at that, take a look at the load diagram for matrix, but at this stage, this would suffice to know that when we apply a load, the primary phase and secondary phase, they share the load. Think of a fabric, and that you are pulling it from each direction, or from two directions, or from four directions, and of course all the stresses would be transferred to all the fabrics and all the fibers. So there's also the reinforcing phase. The reinforcing phase, its function is to reinforce the primary phase that we just discussed. In reinforcing phase, we have the fibers and we have the particles or the flakes, and that's a common shape that we use for reinforcing phase. The secondary phase can take the form of an infiltrated phase in a skeletal or porous matrix. An example is a powder metallurgy part infiltrated with polymers. Let's take a look at physical shapes of an embedded phase. Remember, we already have the primary phase or first phase in place. The possible physical shapes of embedded phase in composite materials are either A, as shown down here, in the form of fiber, B, in the form of particle, or C, in the form of flake. And we are going to take a look at these. So the fibers are usually, imagine these strings that are of much diameter, of much smaller diameters. Usually the cross-section of these fibers are circular. Cross-sections, they vary from very fine, very small ones, 0.0025, very fine one, to a very coarse one, up to 0.13 millimeter in diameters. And this is where we have the opportunity to provide the most of the strength enhancement of composites, because the stresses would be eventually transferred to the fibers, and fibers are those that provide the resistance to the load. Remember that eventually we apply all these materials that we discussed to certain type of loading conditions, and it's very important for us to understand that eventually all the material will be subjected to some kind of loading, different types of loading. So according to that, we need to make sure that we have the robustness for the material that we use it for certain applications. So here's an example of continuous versus discontinuous fibers. You can imagine that we want to embed a layer of fiber, as we already have the primary phase, and we want to now, come up with a one type of a material in which the primary phase and secondary phase, and they are together, and this one material would be subjected to loading. As such, we could have placed these fibers in different directions. It could be in one direction, two directions, or three directions. The continuous fibers are very long, and they should offer a continuous path by which a load can be carried by the composite part. Of course, there are discontinuity at some points, but that's like an overlap, and those also need to be addressed. But in most cases, the fibers are continuous fibers are they don't have any discontinuities. It's just one continuous fiber. The discontinuous fiber, or chopped sections of continuous fibers, they're of course usually shorter in length, with a length to diameter ratio of roughly 100. Let's take a look at three cases of fiber orientations. We can have one-dimensional reinforcement, we can have a two-dimensional reinforcement, and we can have three-dimensional reinforcement. In one-dimensional reinforcement, as the name implies, the maximum strength and stiffness are obtained in the direction of the fiber. Two-dimensional, of course, we are going to have this fiber in two dimensions, and for three-dimensional, then we're going to have composite materials, and in that case, they're in different directions and different layers, and it is easier to achieve isotropic properties versus anisotropic that I just discussed at the beginning of the lecture. So fiber orientations could be one-dimensional, two-dimensional, and discontinuous fiber, as you can see in case C down here. So we can have A, B, and C. In the case of C, you see that these fibers, they provide more like a localized strength when we apply the stresses, and these are continuous in two direction. We could also have them run diagonally, and we could also have different layers. One is over another, and the top layer is in one direction, the second layer is in another direction, and the bottom layer could be in diagonal directions, or you can have them all in one layer. What are some of the materials that we use for fibers? We use glass, carbon, boron, polymers, including Kevlar, ceramics, and metals. Fiber materials in fiber reinforced composites could be any of these depending on the strength, application, and the desired properties. So a second common shape of embedded phase is particulate. Now these are the particles that range in size from microscopic to macroscopic. Usually they are two-dimensional, and they are small, and they are flat. Of course, there are some thickness or height, if you want to call it height, but usually they are flat, and the thickness is not much to be considered three-dimensional. And the distribution of particles in the matrix is random. Of course, in this case, the strength and the properties are close to an isotropic material. Okay, now let's take a closer look at a primary. Let's take a closer look at the primary and how it's been embedded in a matrix. As you can see, the secondary or reinforcing phase of fiber is shown here in the form of a circle, and it is actually shown here. The primary matrix is the foundation, as I keep repeating. This is actually where we apply the secondary reinforcing, and there is an interface between the reinforcing and the fiber itself. Most of the detachments that we see, fiber detaches itself from the primary matrix happens at the location of the interface, because that seems to be where we have much stress concentration when we apply the load. In some cases, we also add a third ingredient here. That is called the interface, but in this case, the interface is actually much larger. And again, with this one, we are going to have most of the issues with, again, debonding of the interface from a matrix itself, and so on. So there are ongoing research on composites, and it is very important to be aware of that, and knowing that they're not really bulletproof, but of course we could have all the bulletproof vests that are made of composites, but it's very important to realize that the research that is ongoing on composites is very interesting to follow. The formation of an interface consisting of a solution of primary and secondary phase at their boundaries are shown here. Again, the primary phase or the matrix is shown here with the lighter brown. The secondary is shown here, like with a different brown, more like khaki, or maybe this one is khaki, depending on the quality of your monitor and so on. The interface, a solution of the primary and secondary phase, is also shown here. Now, it's very important, again, to realize that if we embed the secondary phase into the primary matrix, we cannot achieve the strength that we need if we don't provide these interface and so on. Again, these are ongoing research topics. So that brings me to the end of the slides. Thank you for joining me. If you have any questions or comments, feel free to send them my way via the course website. Thank you.